today's focus will be around gradient descent. So we already know about the neural networks and deep learning basic things, right? And you can see in the image board here that this is a simple two-layer neural deep learning neural network flow. So this is the first layer of the input. There is one hidden layer and there is one output layer. So it's a very simple neural network flow that you can see. Now what we have to understand is how does actual training work. So that is the most important part. Like how, like everyone says that deep learning is basically a black box. No one knows what it does actually. But how it does and how it actually learns things, that we'll get to know when we learn about gradient descent and backpropagation, right? So coming on to the part where we have, let's say, a single neuron. Okay. So assuming we are here, how would you would, in terms of weights and bias, how will you show a single neuron? So this is a basic simple math calculation. So X is an input, Z is an output for us, W is the weight that we want the neural network to know, and then B is the bias. So why do we need bias?
Regarding the bias that we see here, that is B. So in the equation that is Wx plus P, the bias is basically used so that the equation that that deep learning model learns doesn't go through the origin. The reason being, if the input say is 0 and the output becomes also 0, because it goes through origin and there is no bias, right? If we remove the B and we have only the expression y equal to Wx and x becomes 0, then y will definitely become 0. So in cases, for example, for a particular feature, let's say a value is 0, and for that the output should be 10. Right. So for these cases and many other test cases, this would fail. So we need a bias so that these cases are non-there.
And then these actual weights. So weights is what is multiplied with the input, which actually give us the output. So as good as the weight is and as good as the bias is, that would tell us how much good is our neural network in the whole flow. So this is a single neural network, how it the system or how does it looks like, right? Now, if we go back above and see the single layer, the two layer neural network flow, all these three is an input part, these are the hidden layer, and that is the output layer. So what happens normally is we give it some input, then it trains around the hidden layer. It can be n numbers of hidden layer, very large, very some like 4, 10, 10,000 billions of parameters are there. So this is a very simple one. What it has to do is learn the weights around each of these outputs, and then it goes to the final unit and it gives us the output based on the predictability. Now, if we go, how does it actually learns, right? And how does it actually try to learn the weight part here? So if you see, this is a layer 1. We give it some input, let's say X, Y, Z, whatever the input is. It can be very large if there is more than one feature. So we already know in our data set we might have various features, right? So if we say like layer 1, we have, let's say, 3 features. So we are inputting 3 values and we're trying to get 1 value, right? So let's say, for example, we are trying to have some, we have to decide where this particular given stock will go up and down. That's a normal example. So we'll have inputs of, let's say, previous day stocks. We have some data on the news. So we have some geopolitics, right? So all these are inputs to us. And what we want to have is the output, whether it will increase or decrease. So that's the one application what we want to make it learn. So what will happen here is each neurons, as the simple bias function that we have, the input will be multiplied by a weight, and then a bias is added. So the bias and weight, when we start, we choose some random number based on that, any random number we can choose here, and we have to learn what is the best here. So how will we know what is the best? So that is a very simple thing. So what we want to minimize here, say we have an input X which output says that the stocks will increase. Let's say that is the actual output, it should say. And what our model is saying, no, it will decrease. So that is an error, right? Or let's say someone is saying that given this particular person's image, he is of age 18, but actually he is of age 48. So there's an error, right? The actual age is 18. Our network is saying that he is of 48. So what's the error? 48 minus 18, that is our numerical error. That is, there is a difference of 20, right? So how will make our model learn that what is the error? So what we want to do is minimize the error, right? So if we minimize the error, we get the weights and we will try to make it, okay, now our model is best. Now it has learned about the data. So how it actually learns, how we are calculating the weights. So weights is very simple. In simple terms, like I explained, 48 is the age, and then 18 is the actual output that our model gives. So 48 minus 18, that's a simple, you can say there's a difference of 20, and that is an error. But in mathematical terms, if the system is very complex, this is a very simple example that I gave, but normally we have hundreds and thousands of inputs. So in those inputs, we want to try something very particular, right? And there can be multiple things that we want to predict. So in those cases, we cannot just say the error is this output minus input. We have to have some way defining how we are defining the errors. And in most of the neural network images or anything you will see, if we have the best way to define our error, that is the best way our model will train. So there are many ways we can define an error type here. So one of the ways mean squared error. So right, so it's simple. What it does is input minus output squared. That's simple. Why we are doing square here? Because if we just do output minus input and try to get how much error there is, it's just like 18, right? But if we square 18, it will be very big. So what it means here is, if error is small, the square will make it big. So when the error becomes big, the error will try to penalize our model. So error is 10, but you are doing so much wrong that we are saying the error is 100 because we squared 10. So our model, we try to make it low. You are doing very wrong, try to make it better. So if you make our model learn faster. So that is one of the very simple mean squared error that we use in even linear regression and all. So we'll take the same example, let's say. So what happens here in the same flow is, if we go below, right. So if we see here in the above, we saw there was a 2-layer neural network. One was the input, one was hidden, one is the output. So say this is the input 1, right, for the layer 1. This is what we have here. Yeah. So this is layer 1 output. So layer 1 input X will be multiplied by layer 1's weight, and we will get the bias 1. We'll get an output Z from the layer 1 neural network. Then we add a function f. That is why we add function here. Let's say the functions is to add the non-linearity, like tan h function, sigma, that we can discuss later. But it's just to add the non-linearity because our system is very complex and we don't want to just straight line away to train something, a very linear model. So this is the output of, let's say, one layer. In the second layer, we have different weights, we have different bias, but the input is what is the output of the first layer. So that's a normal flow, right? So we get the output of Z2, that is the output of second layer. And then at the last, this Z2 output is put to the last neural network, and that gives us the actual, right? So what happens here is, if you see this particular graph, this is basically the graph of mean squared error that we're talking about. So if we do a derivative of any function, it will create a graph, right? So this is a derivative of mean squared error. So if you see, it is showing that it is going from somewhere up to somewhere in below, right? So what we have to do is minimize error. So in graphical form, to visualize this, a simple mean squared error is that this is its graph when we create a derivative of it. And what we get to see here is, we just have to go from somewhere in between, anywhere, to the minimum point, that is this point. If we can come to this point, that means our error is minimized. And if our error is minimized, our model is performing very well, right? So coming right. So this is a very simple way. That was in form of 3D. This is a 2D graph, so that we can visualize this better. What happens here is, this is a graph of our error function, right? What we want to do is, we start somewhere from here, or we can start from here. Why I'm saying we can start from anywhere is that when I said in the starting, W and B, that for any neural network we start with, is a random number, right? So we can be anywhere in between this graph. We can even be here as well, right? So we don't know where we are. So we start with random, and what we want to do is minimize the error, right? So if you want to minimize the error, this is a graphical form that in maths we create. So what we want to do is, we just want to go step by step below. I will explain why we want to do step by step and not directly jump out here, right? So what happens is, this is a very simple graph, right, for a very linear function. So we are starting here. We take a derivative of that particular function, and what we get is a particular value. Like this is that particular value in form of mathematical equation. What we want to do is, we want to decrease that part from our weights. So if you see here, W was our weight of any neural network, and then DL by DW, this is just a way we show that DL is our graph, W is our weight. So we are saying derivative. What derivative basically means, that this is where you can go max, right? Again, I'm repeating, this particular value will give us where we can go max, and what we want to do is minimize. So what we are doing here is, we are decreasing it from the weights actually, because this will show where we can go max. This is the weights we want to decrease, like our error rate. So we are doing a minus here so that our error decreases and not actually increases. And also you will see there is alpha here, right? So I will explain why we need alpha. Right now we can assume it is 1. So what we are doing is we are taking the derivative, we are decreasing the weight function, and this can be positive or negative, right? So why it can be positive? Such that, let's say, as I said, for example, the age should be 18, but age comes at 48. So if I do 18 minus 48, it becomes negative, right? So negative, there we will get a negative error. We will, from minus and minus will become plus. So basically weight will actually increase. So just in simple terms, weight will increase. Then maybe we come from here to, let's say, here, right? Now here our decreases. So let's say in the next iteration, the output will become from 18 to 30. But still we are again 18 away from our output. The actual output was 48, we are at 30. So we are again an error. And again is always negative. So again weights will increase. So weight increases, we again go to the whole flow and see that, okay, we are again at error, which decreases our error function, and we are slightly moving through this particular minimum, right? Now, if we go and, let's say, actually get the output of 38, let's say that was our answer, right? So if we get the answer of the age, actual days, then error becomes 0. And at that particular place, we have actually trained our model. But actually, it is never right to actually fully train. Like there should be actual error in some place. So what we do is somewhere in between, even if we are here, that is also best part solution here that we can get here, right? Now I will explain what the alpha is here. So alpha is step I want to go. Let's say I'm here, I get an error of 10. I can, let's say I add an alpha 40. So 10 multiplied by 40 will become 400. So what will happen is I will directly jump from here to here. But we don't want that. We overshooted our minimum, right? And now again it can only climb up. We cannot, then again, let's say alpha is 40, right? Then in the next iteration, we get something, let's say value of 58. 58 minus 18 again becomes negative. We again jump back here because our alpha is very big. So we always keep jumping here and there. So we want that is the fine tuning where it comes. When we are training, we want to define based on our inputs and our data set. This is actually learning rate that we call it as written here. So what kind of learning rate we want? We don't want to overshoot it multiple times. It will take too much time to just get to this particular point, and it will never come here because it will keep jumping high, big, and it will never come here, right? So what we want here is to learn that, and even don't want to be that much slow that it takes one step and it rates to one whole day and then it comes to that one. So we have to decide by fine tuning the model what's the learning rate is, right? So that is gradient descent. So what is gradient? Basically, gradient means where is the path, whether it should go down, whether we should go up, right? That is defined by gradient dl by dw. And descent is basically minus sign that we have. We want to descend that path because we want to minimize the error. So we are doing gradient descent to minimize the error, which gives us our weight. And weight is the actual thing that our model size learning, right? That we want to optimize here. And then also there comes the part of backpropagation. What happens? So as I explained, our input was 18. Our input was an image. It goes through the whole network. Then it gives an output of. Then it gives us an output of 30. Let's say it gave us an output of 18, right? So we have 18, right? So this is error. So error becomes, let's say, 38 minus 18. It becomes 20. So now we have to make it learn. We have weights here. We have weights here as well. We want each layer and each neural network to update their weight. So how it will happen? So that is what is called backward pass, or that is backward propagation. So this particular value will help us to go back based on this particular example that I have below. This is the chain rule here, right? So what happens is in the output, we get the output, we calculate the gradient descent. We have the output, then this particular gradient is going back to this particular layer. Then this layer calculates their own gradient, their own errors, and then this particular back propagates to this layer. So this way, whole layer is getting learning everything. Then again our input will come. Now the next output will become 28. Then again the error becomes 38 minus 28. Now we are 10 away from our error. Then again it will try to make it learn all the neural networks, all the weights, everything will update, and let's say hopefully next time we get the output of 18. So now there is no error. So this basically means our model has 100% accuracy on the trained data. Which doesn't make sense that this is good because this is overfitting, but this is what actually happens, the whole flow. This is how deep neural networks or neural networks learns. Backpropagation basically means whatever error we got using the gradient, make it so that all in our back, all the neural network that is there learns it, then again take the input, then calculate the error, then again go back. So whenever you train a neural network, you will see there are iterations going. So that is this particular iteration. One iteration is train, output, get error, go back. Train, output, get error, update weights, go back. So that is the whole one iteration that goes multiple times, and then you get a very good model trained here. So that is the gradient descent which helps us to get the error, and the next backpropagation to actually update out. And this carries on until we get our best fit. So this was the gradient descent. And there is one major issue that's called vanishing gradient. So coming back to some last part that we were discussing was at the last particular layer, what we were doing was getting a particular gradient at this particular layer. Let me go back. Yeah. So what we are doing here is, so at this particular layer, we are calculating the gradient. Then we are calculating the weights and then updating it to the back layer and calculating the same thing here and going to the back layer, right? So what happens is there is a chain rule happening. In the chain rule, what happens is you apply a gradient of one to the another layer by doing a multiplication. Can you see this particular part? So the green is the gradient of this layer. The red is the gradient of last layer. So what this gradient rule of mathematics is, you just want to calculate the gradient of this particular layer directly. We can follow a chain rule. So basically what happens is, in normal mathematical terms, you can say dz multiplied, and then we directly get this. But in form of formula, this is the last value that we get of the last layer. Then this is the value that we get of this layer. If we multiply this, we are getting the weights of this particular layer and then updating it, right? But what happens here is, you see this is a multiplication. And what happens in multiplication is, if you multiply a very small number, let's say 0.5 multiplied by 0.5, it becomes 0.025. So if you keep multiplying, the zeros will keep getting increases and it will become vanishing, right? You will not get anything updated. So the gradient will become 0.000005, right? So if we keep multiplying these small values to the weights, if you just keep getting decreasing, and basically your model is not learning at all. So what happens here is, if we come back here, so this is simplification of each layer. Each layer has multiple neural networks, right? Let's say this is the output layer. We are at last particular layer. Now, the gradient calculated is 0.1, and this is 10 layer, right? And we are multiplying 0.1, 0.1, 0.1, 0.1, that is basically 0.1 to the power 10. And what is 0.1 to the power 10? 0.000001. If we do this particular part, where dl by dw is 0.00 minus 1, where it is getting negligible update, right? Basically no update at all. So our model stop learning. So even if you go from 100 iterations to 1000 iterations, you will not get the performance boot of, let's say, accuracy increase from, it will keep stuck at 50%. It will not go to 60% or 70%. So what the solution of this particular problem, and the issue is here, as I last mentioned, in each layer we are adding an activation function to whatever the output is. So basically we get an output of wx plus b, right? This is added as an input of the activation function. Why we added activation function? So that we get the non-linearity. We don't want to learn linear one line. We need to learn the non-linearity that is there in our data set. Non-linearity basically means the complexity. So let's say images. That is a very complex thing, and we want to learn everything about it. So it cannot be a simple linear function. It will be a very polynomial or very hard function, right? That we want to learn. So that's why we have a activation function. So now again it becomes which activation function we should use and what are the issues with it. So one of the most, in the earlier days of neural network, there was a sigmoid activation function. So what is sigmoid is basically, if it goes from 0 to 1. That's a simple, if you give it any value, it will go from 0 to 1, right? This is the particular graph of its derivative, not the actual function. The actual function of sigmoid goes from 0 to 1. So you put it into something, this is the derivative of it. So now at a particular point, if it anywhere come close to 0, it will remain at 0. So if you use sigmoid as your activation function, it will keep remaining 0. You cannot get even updated with it, right? So that is an issue with sigmoid function. Then also there comes an tan h function. So that's the same issue. Tan h goes from -1 to 1, right, in mathematical terms. But again, if it comes to 0, it is stuck to 0. So that's a issue with that particular function as well. And then there comes a research paper from Microsoft, which was a leaky ReLU. So basically, leaky ReLU doesn't have this particular problem of vanishing gradient, because what it does is the maximum, it will always take the maximum part. So it will never go to 0. Even if it going to somewhere around 0, it will keep the maximum part off. So if you have 0.01 and if you have 0.5, it will pick 0.5. It will not pick 0.1. So it tries to minimize that issue of vanishing gradient so that our model keep learning. It might be that our model is still getting very small learning rates of 0.1, but with this particular function, what we will get is no vanishing at all. So it may take, let's say, not 100 iteration, but 200 iteration, but you will actually get to see that accuracy performance is getting increased, right? So that is also very important part when we are trying to see a vanishing gradient. And again, there is an opposite term for this, that is exploding gradient. So in exploding gradient, again the same thing happens. We are multiplying values. So even if a value is greater than 1, 1.5, right? We multiply 1.5 10 times, it will become very big, right? So if we are multiplying bigger numbers, become very big. So that is also an issue. We will never get to train it, because if it goes such a big numbers, our weights will become very small, because we are doing a minus here, and if this becomes very big, so this will become very small, right? So basically means our model is learning nothing, weights become 0. So that is also an issue. So we have, whenever we're trying to train our models and make it learn, we have to always see what function we should use, what learning we should use, what learning rate we should use based on our data, what activation function we should use, because there are various issues around this, right? And there are various research papers to solve this issue with new functions and all. Yeah. So this was the gradient descent. Hope this was easier to learn. Thanks everyone.